All right, so where we left this on Wednesday, we were talking about transition metal complexes and how the ligands are bonded to the transition metal ion here in the center. So we have an electron deficient transition metal ion, and we have electron rich ligands that coordinate around that transition metal ion in an octahedral fashion. We're going to treat those ligands, we're going to treat these ligands here as point charges in space, meaning that they're going to simply be a source of electron density. Now, that when that electron density is strongly attracted to the positive charge of the cation in the center of the transition metal complex, then what we have is the situation where we get electron repulsion between the ligands and the d orbitals on the metal. So remember that the d orbitals on the metal, and if we're talking about iron, for instance, if we're talking about iron 2 plus, then that electron configuration is argon 3d6. So those d electrons on the metal are in the 3 shell, whereas the valence shell is the 4 shell. And so the d orbitals are not involved in bonding, but they do feel the electron density of the ligands. And so when ligands are bonded to transition metals, we get electron repulsion between the ligands and the d electrons on the metal. The d orbitals, there are 5 d orbitals. Two of those d orbitals, the dz squared and the dx squared minus y squared, have electron density pointed directly at the ligands, meaning that the electron density is directly on the axes. I'm going to draw that here. So electron density directly on the axes. Sorry. Directly on the axes, which means that there is significant overlap between the ligand electrons and the d orbital electrons. Okay. So significant overlap. And this creates strong electron repulsion. The other 3 d orbitals, the dxy, the dyz, and the dxz, have the electron density between the axes. And because the electron density is between the axes, there is less overlap between the d orbitals and the ligand electron density. Okay? So, to summarize what's happening, we have iron 2 plus, and we have 6 water molecules. The metal ion and the 6 water molecule ligands, they are separated in space. They are not attached to each other. That's going to be a high energy system. We're here, this high energy system. When the water molecules bond to the transition metal ion, okay, so this is an electrostatic attraction that creates 6 covalent bonds. Between the iron and the water. We get the metal ion plus the 6 coordinated ligands. So here, let me change color. Here, we now have our octahedral complex. So this is a much lower energy complex than the bare metal ion and the 6 separated ligands, because we formed 6 covalent bonds, and forming bonds always releases energy. But once we've done that, we've formed that complex, now the ligands, the electrons on the water molecule ligands, are now going to create electron repulsion to the d orbitals. And so we're now here. That raises the energy of the system slightly because of that electron repulsion. And the final step is that because the 5d orbitals do not have equivalent overlap with the ligands, the d orbitals split into a set of 3, which are lower energy because they have less overlap and less electron repulsion, and a set of 2, which have stronger repulsion, more overlap, and are higher energy. So we get to here. We have the free ion. When we have the free ion, like iron 2, all 5d orbitals, we have the 5d orbitals are degenerate. I'm going to rewrite that because I don't mean to indicate that those are the 5d, but the 5d orbitals are degenerate when there's nothing bonded to the transition metal. But as soon as we form a complex, and in particular a octahedral complex, those d orbitals, which are not involved in bonding, will split. Okay, and the energy difference between the low energy set and the high energy set, that energy difference is here. We call this the delta O. It's written here as delta OCT for octahedral. I will frequently just write that as delta O, because just to make it even shorter. Delta O is the difference in energy between the d orbitals. Okay, because once we form this octahedral complex, the d orbitals are no longer the same, and we have a difference in energy between them. Okay, so we have the 3 that go lower in energy, and we have the 2 that go higher in energy. These 3 that go lower in energy, each orbital is lower in energy by 40%, or 2/5, 40% of that splitting. And the 2 that go higher in energy by 60% of the splitting energy. Okay, that delta O. The reason this is important is because that overall the energy of the d orbitals has not changed. Okay? The total energy of the d orbitals. So that if we have 3 d orbitals that are lower in energy by 40% of delta O, of that splitting energy, and we have this one is 40%, and this orbital that's 40% of delta O, and then we have these 2 orbitals that are 60% higher, you can see that the total here is negative 120%, and the total here is positive 120%. Those 2 energies cancel each other out. And so that even though the d orbitals have split, overall, the total energy of the d orbitals is the same. Okay, so the reason we started to develop this new bonding model was because we saw that there was a difference between 2 complexes. We said that hexaaqua iron 2, which is here, hexaaqua iron 2 is a paramagnetic complex. Okay, so it is iron 2 is argon 3d6. When we put that into the octahedral complex with the 6 water molecules, the d orbitals split into a set of 3 and a set of 2. I'm going to erase that because it's going to get crowded. And we put 6 electrons. If it's paramagnetic, we have unpaired electrons. And so we're going to have this arrangement where we put 1 electron into each orbital before we pair them up. I'm going to erase the ones that I drew on Wednesday morning, and I'm going to redraw them to show you what I mean by that again, so that we have electrons in, we put 1 in each orbital. That only gets us to 5, and then we have 6. Now we have a paramagnetic compound. Whereas we were told that the hexacyanoferrate 2 is a diamagnetic compound, which means that all the electrons are paired, which means that we must be here where we have all 6 of those d electrons in the bottom set of 3. So why is this true? What is happening? I'm going to scroll to the next slide, and I'm going to make sure I didn't get ahead of myself. So here's what we have to think about. I'm going to draw the d orbital set here. I'm going to say we have an energy level diagram. Okay. And we're talking about, again, iron 2, which is argon 3d6. And we've seen that there are 2 arrangements for argon 3d6. We have the paramagnetic arrangement where this delta O, okay, so again, this energy right here, this is delta O. That's the splitting energy of the d orbitals. If delta O is smaller than what we call the pairing energy, okay, if delta O is smaller than the pairing energy, and the pairing energy is simply electron repulsion. Remember, I've said this many times. When you put a pair of electrons into a given orbital, that the electrons are paired because quantum mechanics says they have to be paired. But paired electrons create repulsion. So whenever electrons are paired, the energy goes up. So there is an energy cost to pairing electrons. So if the delta O, if the splitting energy, the difference in energy between the bottom set of d orbitals and the top set of d orbitals is less than the amount of energy required to pair the electrons, then if you're going to put 5 electrons in here, 6 electrons, then you're going to put 1 in each orbital according to Hund's rule. But then it will cost you less energy to put an electron in the top orbital than it would to go in and pair it up. So we go to 4, we get to 5, and now once we have 5, we try to put 6 electrons in here. Now we have no choice. We're going to put a pair of electrons in the bottom set because that's going to be the lowest energy possibility. Okay, so when the delta O, when the splitting between the d orbitals is low, we have a small splitting. That means that it's going to cost us less energy to put electrons into every orbital before we pair them up. This has a name. This situation is called high spin. So this is a high spin representation. I'm going to change colors. Okay, this is a high spin complex. Again, high spin is when the delta O, when the splitting of the d orbitals is less than the pairing energy. Okay, so if we look at the hexacyanoferrate complex, again, it's an energy level diagram. We have the bottom set of 3, and we have a top set of 2, and I've intentionally drawn that much higher in energy. And now we have a delta O, and in this situation, the delta O is bigger than the pairing energy. What I mean that is, so if we're going to put 6 electrons into these d orbitals, we put 1 into each orbital, like Hund's rule tells us that we would do to maximize that multiplicity, but we've got 3 more electrons that we need to put in. And so it's going to cost more energy to put electrons in the top set than it would be to pair those electrons up, because the delta O, that splitting of the d orbitals, is very, very big. Okay? So it costs us less energy to simply pair the electrons in the lower energy box. And so this is what's known as a low spin complex. So we have two situations with iron 2. We have a high spin complex. Hexa-aqua iron 2 is a high spin complex. It gives us the most number of unpaired electrons. So they have it's a high spin. The spins are not canceling each other out. Okay? Whereas in hexacyanoferrate 2, we have a low spin complex where all the electrons are paired. Now, you need to be able to do this. You need to be able to recognize how many unpaired electrons are going to be in a complex, and you need to be able to recognize, can a complex be high spin or low spin, or both? Can it be high? Is there a choice that we have to make with a high spin or low spin? And I know that this sounds very, very complicated, but it really isn't. Okay, so if we look at all of the d orbital, if we look at all of the transition metals, is what I mean to say. If we look at the transition metals and we start with electron configurations of D1 through D9, and so like titanium 3, so titanium is argon 3D, sorry, 4s2 3d2. That means that titanium 3 plus is argon 3d1, because we removed 3 electrons. We have d1. Okay. If we look at titanium and we have an octahedral complex of titanium, okay, and we have some ligand attached to the titanium, it doesn't matter what it is, it just got a ligand there. That means that the d orbitals on titanium will split. We'll have an energy level diagram. There will be some delta O for that complex of titanium. Okay, this is titanium 3 plus. But there's only one d electron. And so if we're going to have one d electron, it's going to go into the lowest energy orbital. And so titanium 3, a D1 metal, we don't worry about high spin and low spin. There's only one possible configuration. Same thing for vanadium. Okay? In vanadium, we have, I'm going to quickly draw a vanadium 3 octahedral complex. So we have a vanadium 3 octahedral complex. The d orbitals split in that vanadium 3. We have some splitting energy, but this is a D2. And so Hund's rule says we're going to maximize the multiplicity. We're going to put one electron into each orbital before we pair them up. And again, there's only one possible configuration. I'm going to leave it to you to show that the same thing is true for D3, like chromium 3. There's only one way to do it. So in reality, there's the only choice we have to make of whether or not a complex is going to be high spin or low spin is for D4, D5, D6, and D7. And I'm going to use this phrase a lot when we talk about this. So a transition metal that is D4. What I mean by that is that we've removed the s electrons, and what's left beyond the noble gas core is 4 d electrons. It's a D4 metal. A good example of that is manganese 3 plus. Okay, manganese 3 plus is D4, and so depending on the conditions, D4 can either be high spin, where we have one electron in every orbital in the bottom set of 3 and in one of the top sets, or we have a low spin situation where all 4 electrons are in the bottom set of 3. Okay? A D5 metal can be high spin or low spin. D6, as we've seen with iron 2, can be high spin or low spin. It can have 4 unpaired electrons, like high spin D6, or it can have no unpaired electrons, like low spin D6. And D7 can be also high spin or low spin. Okay. D8 and D9, like nickel and copper, again, there's only one way to do that. Again, that's something I'm going to leave that to you to show that when you split the d orbitals into a set of 3 that are low energy and a set of 2 that are higher energy, and you try to put 8 electrons into there, there's only one way that you can put 8 electrons into 5 d orbitals. So there's only one configuration. Okay, so D4, D5, D6, and D7. Those are the only situations where we have to worry about high spin versus low spin. So let's look at how do we predict, how do we know if something is going to be high spin or low spin? Well, the first rule is actually very, very easy. Only the first row transition metals exhibit high spin. Okay. Second and third row transition metals are always low spin. So this means that the only ions that we are interested in about figuring out whether or not it's high spin or low spin is manganese 3, manganese 2, iron 3, iron 2, cobalt 3, cobalt 2. And I just saw a typo up here. I'm going to correct it right here. That is not cobalt 3. That should be cobalt 2. Cobalt 2 is D7. So those, we're only interested in manganese, iron, and cobalt. And we're only interested in the +2 or +3 oxidation states. So those are the only metals we have to worry about. A good example, so just under, if you look at a periodic table, I don't actually have a periodic table that I can pop up very easily and show you this, but under cobalt is the element rhodium. Okay, so if we look at cobalt 3 and we put 6 water molecules around the cobalt 3, okay, that's going to have a 3+ charge. We show the energy level diagram, the d orbitals split in that energy level diagram. Cobalt 3 here is D6, and so this is actually, cobalt 3 is going to be just like iron 2. It's going to have 4 unpaired electrons. It's high spin. Okay. If we did the same thing with the element right below cobalt, which is rhodium, okay, and I'm going to put the 6 water molecules in there, and we talk about hexa aqua rhodium 3, and we draw the energy level diagram, and we put the electrons into rhodium. Rhodium 3 is actually low spin. Okay, so only the first row transition metals and only manganese, iron, and cobalt. For our purposes, those are the only metals that are going to be either high spin or low spin. Okay, if it's a second or third row transition metal, like rhodium is in the second row transition metals, it's no matter what the complex is, it is low spin. Okay, so other examples. Metals with high oxidation states are going to tend to give low spin complexes, right? I'm going to explain this very, very quickly. So high oxidation numbers mean a large positive charge, which means that those metals are very electron deficient. I'm going to actually write that. Very electron deficient. So they're going to have a very strong attraction to the ligands. Okay, so if the metals are very electron deficient, they're going to be very strongly attracted to the ligands, which is going to mean that the ligands are pulled close to the metal, which increases the ligand to d orbital electron repulsion. And if we have large electron repulsion between the ligands and the d orbital, the final thing is that makes for a large splitting energy, a large delta O. And if you have a large delta O, that's going to give low spin complexes. Okay, so I'm going to summarize that again. I'm going to go back through that. We have metals with high oxidation numbers, meaning that they're very electron deficient. Metals that are very electron deficient are going to be strongly attracted to the ligands because the ligands are electron rich. So if the metal is strongly attracted to the ligands, then the ligands will be pulled close to the metal. And as the ligands get closer and closer to the metal, they're going to overlap more with the d orbitals that are present, and that's going to create more repulsion, stronger electron repulsion. And the more the electrons are repelling each other, the farther the d orbitals will split from each other. And so we get large delta O's, large splitting of the d orbitals. That gives us a low spin complex. That's actually the reason also for up above why the second and third row transition metals are also low spin. Rhodium, I'm going to see if I can draw this here. Let me pick a different color. Okay, so in cobalt, just for instance, I'm going to draw one orbital. I'm going to draw like the dz squared orbital in cobalt here. You can see that I'm just drawing this not to any sense of scale, but because that's a 3D orbital, it's pretty small. But in rhodium, that's going to be a much bigger orbital because rhodium, the electrons are farther away from the nucleus. Okay, and so in rhodium, the d orbitals are bigger than they are in cobalt, which means that the d orbital electron density is going to be farther away from the nucleus. It's going to actually be closer to the ligands. So the d orbitals are closer to the ligand. Okay, and again, if the d orbitals are close to the ligands, we're going to have strong electron repulsion, which is going to lead to a larger delta O, which is going to give us low spin. Okay. So the last thing, those are fairly straightforward. I guess that's the only way I can put that. Those are there in those instances. The first two bullet points here about whether or not something is going to be high spin or low spin, those are not decision points. Okay. Only manganese, iron, and cobalt are going to be high spin or low spin, but that doesn't tell us whether or not it is high spin or low spin. Things that have high oxidation numbers are going to be low spin. Okay, so again, that's not a decision point. We're not predicting anything. So how do we predict whether or not manganese, iron, or cobalt complexes will be high spin or low spin? And so the major determining factor here is the identity of the ligand. Okay? It is the ligand that is attached to the metal that has the major factor in what the splitting of the d orbitals is. And so this is the one time, well, I don't want to lie about that. This is one of the rare times when I'm going to give you a list of things, okay? And the list is important. And your natural inclination is going to be to try to memorize this list. Okay? I don't want you to memorize this list. This list of ligands is what we call the spectrochemical series. So we're right here, the spectrochemical series. This is a list of ligands that are ranked, that are put in order of the amount of repulsion that they create with d orbitals. Okay, and so the common we've got them ranked here, and so that iodide has the weakest repulsion with the ligands, and carbonyl has the strongest repulsion. Okay, and you can see that we have the most common ligands everywhere in between. Here, I'm going to say this again though. Do not memorize this list in order. Okay, two things I'm going to point out about this list. One, I have intentionally presented this list such that there's a line there's ligands that are on the top line and ligands that are on the bottom line. Okay, ligands that are on the top line have weak repulsion. All of these ligands up here have weak repulsion. And in fact, what we refer to them as, we call these weak field ligands. Okay, weak field ligands, and weak field ligands give high spin complexes. So all of these ligands on the top row, iodide, bromide, thiocyanate, chloride, nitrate, fluoride, hydroxide, oxalate, and water, those are weak field ligands. They give high spin complexes, meaning that they do not interact strongly with the d orbitals. Therefore, the splitting of the d orbitals is very small, and it costs us less energy to put electrons in every orbital before pairing them. The ligands at the bottom here, on the bottom list, have very strong repulsions, meaning that these ligands at the bottom, ammonia, ethylene diamine, nitrite when it's bonded through the nitrogen, cyanide, and carbonyl, those ligands interact very, very strongly with the transition metals, and they have strong repulsions, which makes them strong field ligands, which would give low spin complexes. Okay, so that's the first thing about this list, is that the ligands on the top are weak field ligands that give high spin complexes. The ligands on the bottom are strong field and give low spin complexes. And so now you're going to be tempted to simply memorize the top list as weak field and memorize the bottom list as strong field. I don't want you to do that either. It's even more simple. Weak field ligands bond through oxygen or a halogen. Okay, so we've got iodide, bromide, thiocyanate. Okay, so thiocyanate is, as I said 100 times so far, chemistry is the science of exceptions. But thiocyanate is clearly not oxygen, nor is it a halide. But I don't know how to say this other than it's classified as a pseudohalide. Thiocyanate, which is right here, thiocyanate behaves just like a halide. So it's in between bromide and chloride. It behaves just like that. You're just going to have to trust me. I'm not going to ask you that. I'm not going to put thiocyanate on the exam and have you try to remember that that's weak field. I'm not going to do it. Okay? So everything else, ignore the thiocyanate. Iodide, bromide, chloride, nitrate, fluoride, hydroxide, oxalate, water, all of those ligands either bond through the oxygen or they bond through the halogen. Those are weak field ligands. Strong field ligands bond through nitrogen or carbon. If the atom bonding to the transition metal is a nitrogen or a carbon, and you can see that these here bond through nitrogen, and carbon monoxide and cyanide bond through carbon, those ligands are going to be strong field ligands. And so all you need to know, here's what you need to know. I'm going to give you some transition metal complexes. They're going to have ligands attached to them. You're going to say, are the ligands bonded through oxygen or are they halide? If that's true, then it's going to be a high spin complex. If it's manganese, iron, and cobalt, or you're going to look and say, is it bonded through nitrogen or carbon? And then you're going to say, okay, that's a low spin complex. I will never give you a complex that has mixed ligands, that has a weak field ligand and a strong field ligand in the same complex. That's off the table. I'm not going to do that. I'm also never going to ask you to compare two weak field ligands to each other. I'm never going to ask you which is weaker, chloride or fluoride. I'm not going to do that. I'm not going to ask you which one is stronger, carbonyl or cyanide. That's off the table. What I could do is ask you which is stronger, carbonyl or water. Okay? The strong field ligand has a stronger repulsion than the weak field ligand. Okay, that's fair game. Comparing weak to strong is fair game, but I'm never going to ask you to compare two weak field ligands. I'm never going to ask you to compare two strong field ligands, and I'm never going to give you a complex where they are the same, where they're mixed, I guess is what I mean to say. Okay, so what I want to do is I want to go back up to those complexes that we drew and named at the beginning of class on Wednesday. So bear with me as I scroll through. And I want to do what I said we were going to do. I want us to figure out how many unpaired electrons are in each of these complexes. So I'm going to pick a color that we haven't used yet. Okay. And we're going to start here with iron 3. Okay, so we have iron 3. So iron 3 is argon 3d5. So that's a d5 metal, that's iron. So this complex could either be high spin or low spin. And so if we draw our electron diagram, we're going to put our 5d orbitals there, and we're going to look and say, well, fluoride is weak field and water is weak field. And so we have weak field ligands attached to the metal, so this is going to be a high spin complex. And so high spin d5 is 1 electron in each orbital. That's 5 unpaired electrons. Okay, so remember, on the exam in a little less than 2 weeks, I'm going to give you a chemical formula. I'm going to ask you to name the complex using standard nomenclature. I'm going to ask you to draw the complex and all possible isomers, and I'm going to ask you how many unpaired electrons are in the complex. So in this triaqua trifluoro iron 3, we have 5 unpaired electrons because the ligands are weak field, and that gives us a high spin D5 complex. Okay. If we look at nickel, this is nickel 2. So nickel 2 is argon 3d8. I'm just blowing through that. I'm going to trust that you can do that. If you can't write the electron configuration for an ion, you need to learn to do that. This is non-negotiable. You have to be able to do that. As I said, if you can't get that right, nothing else you're going to tell me is right. Okay, so you have to be able to get that right. So remember, always remove the 4s electrons or 5s electrons or whatever. Remove the s electrons before d electrons. Okay, so that's 3d8. 3d8, remember, is not one of the ones that can be high spin or low spin, so we don't actually even care what the ligands are. And if we look at d8, we can do 1, 2, 3, 4, 5, 6, 7, 8. That's the only possible configuration for d8, and so that's 2 unpaired electrons. d8 will always have 2 unpaired electrons. It does not matter what the ligand is attached to it. Okay? We go to copper. This is copper 2, as shown there. Copper 2 is argon 3d9. Okay. Argon 3d9, again, d9 is not a electron configuration that shows high spin, low spin. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That time I went up, I put 1 in each orbital just to show you that it doesn't matter how you do it. You can only get one configuration. That's one unpaired electron. Okay? Now, the last one here is diamine dichloroplatinum 2. That is the square planar complex. And so everything we've talked about here with high spin and low spin and the splitting of the d orbitals, we've only talked about octahedral complexes, and you are only responsible for octahedral complexes. Okay, we're not going to talk about how electrons split in tetrahedral complexes. We're not going to talk about how the orbitals split in square planar complexes. That's much more complex. That's advanced in organic chemistry, and so you're not responsible for that. So we're not going to show you for this diamine dichloroplatinum. Okay, so iron 3 here shows facial and meridional isomerization and has 5 unpaired electrons because it is a high spin complex. The hexaamine nickel 2 is 2 unpaired electrons because it's D8, and trisethylene diamine copper 2 has 1 unpaired electron because it is D9. And that's the only possible configuration. All right. This is really, really complex, and I totally understand that. And at this point, if you're still with me, and I hope you are, you're probably sitting there going, boy, this doesn't make a lot of sense. I'm not entirely sure what's going on. But I mean, how do we even know that this is like true? How did this theory is whack? So how do we? Yes, I just said whack. I don't know why I said whack. This theory. How do we know it's true? And so you always have to make sure that experiments verify your theory. Can we perform experiments that match our theory? Okay, so the first thing we want to show is what are the successes of this theory. By the way, this bonding theory is called crystal field theory. And so how do we know that it's true? How do we know that this is what's happening? Well, the first thing, and we've talked about this over and over, is that crystal field theory, this bonding model, the splitting of the d orbitals, accurately predicts and explains paramagnetism of transition metal complexes. It allows us to say that hexaaqua iron 2 is paramagnetic because it has weak field ligands which give high spin complexes. Okay, and conversely, hexacyanoferrate 2 is diamagnetic because cyanide is a strong field ligand which gives a low spin complex. Okay, so, and we can measure that, right? I mean, we can perform that experiment. We can measure the number of unpaired electrons in a compound by simply weighing that compound in a magnetic field. And remember, paramagnetic ions are attracted to magnetic fields, and diamagnetic compounds are weakly repelled by magnetic fields. So if you put a compound of hexaaqua iron 2 in a magnetic field, if you weigh it in a magnetic field and then you actually turn on the magnet, then when the magnet is on, the iron compound will appear to be more massive, will appear to be heavier because it will be attracted into the magnetic field. Whereas if you have a hexacyanoferrate 2 and you weigh it and then you turn on the magnet, then it will appear to weigh less because of the repulsion. So we can do that. We've talked about that before. Other things that crystal field theory allow us to explain, and this is a very, very important idea. If you think to the labs that you've been doing, like with the vanadium and chromium and iron and cobalt and nickel and copper, in fact, all of the metals, just about all of the metals that you've been working with, all of those transition metal compounds have high color. They're highly colored, very intense, vibrant colors. So where does that color come from? Okay. The first thing we need to recognize is that color comes from the absorption of light. Things are colored because they absorb certain wavelengths of light. So let's look at hexaaqua titanium 3. Okay, it says it's purple, so I'm actually going to draw that in purple. Okay, so here's hexaaqua with a 3+ charge. Okay, and if we draw the energy level diagram, and this is D1, titanium 3 is D1. We have this configuration. Whereas titanium hexachlorotitanate 3 is yellow. I don't have a good yellow pen. It would be too light to show up. I'm going to do this in orange. Okay, hexachlorotitanate 3. Now, I told you on the exam, I'm not going to expect you to know this, but because we saw the spectrochemical series above there, you can see, I'll scroll up, you can see that in fact chloride here is a weaker ligand than water. So that means that chloride is going to give it's going to have weaker repulsion, and it's actually going to have a smaller splitting energy, but it is still D1. Okay, so let's talk about how does this relate to the color. So molecules or any substance has color when light comes in, and we typically show light by a squiggly line, and we put H nu on that squiggly line. Okay, so that tells us we have a photon of energy. Remember from whatever science class that you had where you saw this, that the energy of light is equal to Planck's constant times the frequency of the light. I'm not going to ever ask you about that. I'm just not going to test you on that, but that's how we designate light. We say that light has an energy. That energy is equal to its frequency. Okay, so light comes in. If the energy of the light is equal to the splitting energy, okay, if the energy of the light equals the splitting energy, then the electron will absorb that energy. Okay? The electron, the light comes in, it hits the photon, it has that photon hits the electron, that photon, that light has the proper energy, has the same energy as the delta O, and so the electron can absorb that energy and go to the excited state here. Okay? We put an electron up in energy. And to do that, we have absorbed some light. And so that's what this graph here is. This is called we call it a UV visible spectrum. And you've already taken a UV vis spectrum. You've done it lots of times by this point, but we actually did it in our own lab when we did that nickel ammonia complex, that hexaamine nickel 2 chloride complex, which we've been talking about. And that's the complex that you made. To analyze the concentration of nickel, you actually used a spectrometer, used a UV vis spectrometer. And so what you were doing was you were measuring the energy of light that causes an electron in nickel to go from the ground state to the excited state. Okay, and so this particular diagram, this particular spectrum here, is the spectrum of titanium 3 plus. It's actually of hexa-aqua titanium 3. So I'm going to actually write that. This is the spectrum for hexa-aqua titanium 3. And you can see that it actually, the wavelength of maximum absorption is just above 500 nanometers. Okay, so that's kind of green light. Okay, 500 nanometers. Why don't I actually make that green? Okay, so hexa-aqua titanium 3 strongly absorbs green light. Okay, because this delta O here, the splitting in hexa-aqua titanium 3 is approximately 520 nanometers. Okay, to match this line right here. That the splitting energy of the d orbitals in titanium 3 is the same energy as green light. And so the electron in titanium absorbs that green light. Well, if you are removing green light from the visible spectrum, then what passes through is blue and red. You're removing the middle of the spectrum. The blue light from visible keeps going through. The red light from visible goes through. And so we get purple. Our eyes perceive purple. So if titanium strongly absorbs green, that means blue and red light pass through, or the technical term for that is are transmitted. And we see purple. Okay, because we've seen the blue and the red light. Okay, we are not reflecting light, we are not emitting light, we are simply, our eyes are perceiving what colors of light are allowed to come through, to be transmitted through the solution. Okay, and because green is being removed, we are seeing red and blue, which gives us purple. Now, if we look at the hexachlorotitanate here, in this case, we can see that the delta O for TiCl6 3 minus is a lower energy than the delta O for hexa-aqua iron 3, which means that titanium 3, the hexachloro complex, is going to absorb lower energy light. Okay, and as it absorbs lower energy light, it's going to start to absorb now in the yellow and in the orange. It absorbs closer to orange, the closer to the orange red light. And what is transmitted through is the yellow, green, and blue light, which when those are mixed to us appear yellow. Okay? If we're taking orange out of the spectrum and some red and some yellow and some green and blue and purple get through, our eyes perceive that as yellow. In fact, it's kind of a dirty brown yellow. But that color of that complex is a function of the energy of the splitting of the d orbitals that tells us what color of light is being absorbed. Okay? We will come back to this. We'll see this a couple other times where we'll talk about the colors of things and how it relates to the splitting of the d orbitals. Okay? And then the last thing that I want to talk about is how do we know that this is in fact true? How do we know that the d orbitals do in fact split? Is we can do one more experiment, and that experiment is where we can measure the enthalpy of hydration for the transition metal complexes. Okay, so remember that we're going to take a metal ion that has a 2+ charge. It's in the gas phase, and we're going to add 6 water molecules in the gas phase, and we will get hexa-aqua complex of that metal ion. And the energy of that reaction is called the hydration enthalpy. Okay? It's always going to be exothermic because we're making 6 covalent bonds, so that's going to release energy. It's going to be highly exothermic. And if we were to look at this solely as a function of charge density, and remember that hydration enthalpy is a function of charge density. Okay. Hydration enthalpy being a function of charge density, as charge density increases, we get stronger bonds to the ligands. We're going to release more energy. We're going to have a larger hydration enthalpy. And so that's what this dotted line shows. This dotted line is the predicted hydration enthalpy based on charge density for the 2+ cations of the first row transition metals. Okay, so this, in fact, for all of period 4. So we start here at calcium 2. We get calcium ions. So calcium has +2. We're missing one here between calcium and titanium. That would be scandium, but scandium does not have a 2+ ion. That's unknown. So we've skipped that. But we get into the transition metals, so titanium, vanadium, and chromium, manganese, iron, cobalt, nickel, copper, and zinc. All of those metals have well-known and well-described 2+ cations. And so remember that as we move from left to right across a period, the effective nuclear charge increases, which makes the ions smaller, which increases charge density. Okay, so zinc has a much higher charge density than calcium does. Okay, so this is high charge density. I don't want to, let me rephrase that. I don't want to confuse the issue. I'm going to hedge my bets. This is higher charge density. And this is, calcium has a lower charge density. And you can see that zinc has a much more negative, much more exothermic hydration enthalpy than calcium does because of a higher charge density. Okay, and so that dotted line predicts what the hydration enthalpy would be if it was based solely on charge density. The blue line is what the experimental hydration enthalpy actually is. And you can see that it has this very characteristic shape that we actually call the double humped phenomenon. Okay, because there are two humps on there. And what we see is that the hydration enthalpy, that there is extra energy released when these complexes are formed. Okay, I'm going to write it here. Experiment shows us that extra energy is released when the octahedral aqua complex is formed. And so what is that energy? Where does that energy come from? That energy comes from the splitting of the d orbitals. Okay, I'm going to scroll down here. I'm going to show this quickly, and then I'll go back up to the diagram. So we have energy level diagram. Okay, titanium 2 would be D2. So this is delta O. And so we would have this situation for titanium 2. But remember that these orbitals are 40% lower in energy than where they started. Then those orbitals are 40% lower in energy than if they would be in the bare transition metal ion. Okay, and these orbitals up here, which don't have anything in them, are actually 60% higher than they would be. 60% of the splitting higher than they would be without any ligands. And so by splitting the d orbitals, we get a net stabilization. We actually are releasing 80% of delta O. Whatever this splitting energy is, when we form the octahedral complex, we're actually releasing 80% of delta O by splitting the d orbitals. And so we're releasing even more energy. Okay, the electrons, the orbitals started here in the free ion, and then we split them into a set of 2 and a set of 3. And by putting electrons in the lower energy, we are actually releasing energy. Okay? And so if we go back up to the graph, we can see that calcium, the experimental value for enthalpy of hydration, matches our predicted value because calcium has no d orbitals, has no d electrons. And so splitting the d orbitals and there's no electrons to put in there, so there's no increase in stability. But in titanium, here we have dropped below predict. We've released even more energy because we are now 80% of delta O. And when we get to vanadium, that's 120% of delta O because now we're at D4. Sorry, not at D4. We're at D3. So this is D2, D3. When we get to D4, remember this is the aqua complex. So it is high spin. High spin D4 is minus 120 plus 60. That goes slightly up because now we're only minus 60% of delta O. And then we get to manganese, which is D5. D5 has no net stability because in a weak spin, D5, those electron energies cancel each other out. And so now manganese 2, our experiment matches our predicted. And then we go back to iron. That's minus 40% of delta O, minus 80% of delta O. Nickel gets us down to minus 120% of delta O. And then copper, again, we're back to minus 60% of delta O. And then we get to zinc, and zinc is D10. D10, all the electrons are paired. And we have no net stability. Okay, so we get, this is again proof, experimental proof that the d electrons do split in an octahedral field, because when we measure values, when we measure energy values like the hydration enthalpy, we get more energy released than we can explain solely based on charge density alone, solely based off of bond energies. There's more energy released, and that energy comes from splitting the d orbitals and putting electrons into lower energy orbitals. Okay, I'm going to stop there. That is the end of chapter 19, Introduction to Transition Metal Complexes, and that is also the last of all the new material for this class. We're not going to learn anything new for the rest of the semester, but we are going to apply what we have been learning: effective nuclear charge, charge density, lattice energy, hydration enthalpy, hard soft acid base, and while we're still talking about transition metals, we will talk about the splitting of the d orbitals. Okay, but that's it. We're going to just use those for the rest of the semester, and we're going to start talking about the elements group by group, and talk about what they do, what's interesting about them, and I'll start that with my next recorded lecture, which I will post sometime before Monday. So with that, I'm going to save this. It's going to take a while to save. And as soon as that saves and I can get back to my lecture capture software, I will stop the recording. And so have a good weekend.